Good morning. Today we're going to be looking at the force of gravity and a little bit more into free fall notes. Some of this stuff we've looked at in the lens of kinematics, and today we're going to be looking at it through a different lens, through dynamics lens. Everything on Earth experiences the force of gravity. And gravity, as we know, exerts an acceleration of 9.8 meters per second squared on all objects on the surface of the Earth. Often we're going to be using the symbol g, and you would have seen that recently in a video that you watched, to represent the acceleration due to gravity. This is a constant for all bodies near the Earth's surface. Unless otherwise stated, we will assume the force of air resistance is 0. Otherwise, our calculations will become very, very difficult. So let's just jump into it and try a couple questions. Number 1 is determine the force of gravity acting on the following objects. A 32 kilogram cat. Now this might not be your regular domestic cat, a house cat. I'm not sure about you, but I don't know many house cats that weigh 32 kilograms. If we're looking for the force of gravity, we're going to be writing it as Fg, similar to the formula over here. Fg is equal to mass times gravity. We were looking prior at the formula force is equal to mass times acceleration. Well, acceleration due to gravity, g, is 9.8. And so we can exchange the a for a g when we're looking at force of gravity. So this is just a general force here. We're talking about the specific force of gravity, mass times gravity. So Fg is equal to mg, which is equal to 32 times 9.8. So what we end up getting is 313.6. If we have two significant figures, our final answer is going to be 310 newtons. And that is our final value right there. Force of gravity acting on it. And the force of gravity is acting in the downward direction. 12 kilogram eagle. Again, I'm not sure if this is a big eagle or not. It seems like it is, but I'm not sure. I'm not well versed on eagles. 12 kilogram eagle that's soaring 12 meters per second over the Grand Canyon. So if we're looking for the force of gravity, this time let's just plug in our values. We know it's mg, mass times gravity, so it's just going to be 12 times 9.8. So approximately 120. Actual value is 117.6, but once we round to two significant figures, this is going to become 120 actually, coincidentally enough. And again, the force of gravity is downwards. We have a 145 gram baseball falling after a pop fly. We will be converting the grams to kilograms. So there's 1,000 grams in a kilogram. So we move that 3 decimal places over. This is the same thing as 0.145 kilograms. So divide by 1,000 or move it 3 decimals to the left. We'll multiply this by 9.8. We're going to get 1.421, and in this case 3 sig figs, so we can have a final answer here of 1.42 newtons downwards. And lastly, 75 kilogram bench press being pushed up with an acceleration of 0.25 meters per second squared. So again, if we're looking only at the force of gravity, not the applied force, which is pushing this bench upwards, our force of gravity is still going to be whatever the mass of the object is, multiplied by acceleration due to gravity. We get a value of 735, and when we apply the two significant figures, which we find here, that will be 740 newtons in the downward direction, like so. For number 2, draw a force diagram on the following where each force has a magnitude labeled. We have a kid pulling a 25 kilogram wagon 24 newtons east of force, as well as a net force of only 2 newtons. So pulling hard to the right or hard east, but only actually exerting a total net force of 2 newtons. So in order for that to be the case, there's going to be some opposing force. If we have an applied force of 24 newtons, but there is a net force of only 2, that means there has to be a force in the opposite direction. that isn't mentioned here, which would be the force of friction. The force of friction. So what do we have here? We have a kid pulling a wagon. Kid pulling a wagon. All right, so I guess we can have it one of two ways here. He is really, I'm not sure what he's doing there. Lifting his leg up. Okay. As he's pulling this way. So here's wagon. Really low rider. Off he's going in this direction. We have our force of friction in this direction. Force applied. And then we also have our net force was a little bit this way. F net being 2 newtons east. We have force of friction, which we'll calculate in a bit. Kid pulling it with 24 newtons of force. So there's clearly something going in this direction right over there. So if we first, after drawing the diagram here to the best of our abilities, we're going to say our net force is whatever applied force is, because our applied force is going this direction, our net force is going this direction, minus the opposing forces. Force of friction is going in the opposite direction, so we're going to represent negative force of friction there. And we want to rearrange this to determine, okay, well, what do we actually have for our force of friction in this particular case here? Let us rearrange it so that we can actually solve for force of friction here. We'd add it to this side, subtract net force on the other side. And we're going to get applied force minus our net force, equaling our force of friction. And if we plug in our values now, our applied force was 24, our net force was 2, and so our force of friction is going to be only 22. And let's keep it as 22 by just whatever else, going decimal 0 with the net force, 2.0. And technically, I guess if we're only adding and subtracting this question, we would still have this number, the value of the smallest place value, so 22 newtons, so I guess it wouldn't matter there. And what direction? This was to the west. To the west. So 22 newtons to the west. Make sure to include your direction. For B, we have a 21 kilogram goat falling out of the clutches of a golden eagle, accelerating at a rate of 8.4 meters per second squared towards its demise. So in this case here, normal gravity would accelerate this falling goat at 9.8. It's only at 8.4, meaning that there is some force of friction, or aka wind resistance, that's going to be slowing this goat down. So again, I'm not even going to try to draw goats. This is just going to be goat, G. Here's my eagle who dropped goat. And now there's the force of gravity on this goat. And there's a force of friction due to air resistance over here. So usually you will want to start off by saying what is your net forces in this question, and we've drawn it out ready to kind of get a better picture as to what is actually happening here, because dynamics, again, it begins to describe motion as opposed to kinematics where you're actually just calculating straight out what is happening here. So we want to know a little bit more of like what's the situation going on here. Well, we have our force of gravity down, and then minus whatever's opposing that, the force of friction. And the net force, we also know, is equal to mass times acceleration. At this point here, we could then go ahead and rearrange this to figure out, well, what is our force of friction? If we know our force of gravity, or at least can calculate it, and we've been given our acceleration and given our mass, we can actually solve for force of friction. So bring force of friction to the right, bring mass and acceleration to the left by adding this over here and subtracting the mass and acceleration on the other side. So it's going to be Fg minus ma. And force of gravity is the same thing as mass times gravity. And now we can just plug in our values. So the mass is 21 times gravity 9.8 minus 21 times 8.4. So it's really 21 times the difference here, 1.4. 21 times 1.4. Force of friction is 29.4 newtons. And if we look over here, 2 sig figs, we will have our final value of 29 newtons in the upwards direction over here. Michael and Dwight are dropping watermelons from the roof of the office. That might have been fun to try out of our school too. So if anyone has the chance to maybe buy a watermelon, want to drop it from our school, second story, maybe we can take a look at that. Although whoever drops it will have to clean it up, just an FYI. Anyways, it's 7 meters above the ground, so it's a lot taller than whatever our second story is here, which some people calculate it to be approximately 4 meters or so. Here it's 7, so almost double. How long does it take the watermelon to splatter? Well, how long did it take our water balloon to splatter? It was about less than a second. So at 7 meters here, probably just a little bit more than a second. Not by much, because again, with every moment that passes, that watermelon continues to increase in velocity, and it will take less time to travel a further distance. So even though it's almost doubled in displacement, it's not going to take much longer to travel that extra little bit of distance once it's already been accelerated by 9.8 meters per second every second. So even with dynamics, there are times in which we will go ahead and use TAD-VV to go about our day. And we can now plug in our values of what we do know, if there is anything here. We do know that acceleration is negative 9.8. We know that our displacement, we'll be able to figure that out in a moment. Our initial velocity, if it was dropped, is 0. So let's go to displacement for a moment. So if you have an office and here you are, you're Michael dropping this watermelon out the office. Here's 7 meters over here. This is the final point. Your final point, this is your initial displacement right over here. So traditionally, we use the ground as our reference point, representing 0. Here, this would be positive 7. So if you wanted to actually say, well, what is your change in displacement? Final minus initial, that's going to be 0 minus 7, which is negative 7. You could also think of it in a different way too. So yes, you don't have to do this math. I'm just showing you that the math works. The other way is just to say, well, if you start here and end here, you have displaced 7 meters down representing negative. So we would have negative 7 meters for our displacement. Be aware of that. That can really change up your answer. That could cause you to have a negative value for time if you just created a positive value for displacement instead of a negative value. Very important to be consistent. If acceleration due to gravity is downwards and we represent it with a negative, then you also have to represent the displacement as negative as it goes down as well. Now we look for the formula that does not include final velocity. And if you remember it, it is displacement is equal to initial velocity times time plus 1/2 AT squared. And this first part is going to cancel due to VI being 0, so that part cancels out. And now it's going to be a little bit easier to arrange the formula here. So if we're going to be solving for time, there's no t over here, just t squared. So we're going to multiply both sides by 2, divide both sides by a, and what we're going to have is t squared being 2d over a. And if we want to get just t, then we would take the square root of that in the end there. So I know I'm jumping a bunch of steps. If you really wanted me to, we could go ahead and show you those quickly. It's 2 equals that, 2d over a equals t squared, and then there you go for your final step. I'm not even going to write the plus and minus because time is going to just be positive. Plug in your values now. 2 times negative 7 over negative 9.8. The negatives will cancel. It's going to be 14 over 9.8 in the end. And take the square root of that value. You're going to have 1.2 seconds. So just a little bit more than we had calculated for the height for the water balloon droppage. And then secondly, it says how fast is the watermelon going at the bottom? Well, this time we're going to be using final velocity, and since we have every single other value, we can really choose any particular situation, well, any formula that is to use. And I'm just going to go back one step here. If we're looking at our time, it was 1.195, and so we used 1.2. So if you were to use time in your formula for the next question, I would want you to use 1.195, not 1.2. So well, I guess it could be 1.20. So yeah, technically it'd be 1.20 if you rounded to 2 decimal places. So in this one case, it would be okay, but just be aware of that. I'm just trying to highlight that intermediate steps, you're going to be using 1 extra decimal place. So in this case, it'd be 1.20, which actually doesn't change anything. So whether it's 1.2 or 1.20, but sometimes it does, and you have to be aware of when it does. So even if you wanted to write 1.20 up here, and then here's your final answer over there. So if you were using values, you'd use them from here. I'm going to choose my favorite formula to solve. It's going to be VF squared is equal to VI squared plus 2AD. And I'm going to take the square root of VF and the square root on this side as well. When I take the square root, I'm going to go plus or minus because the final velocity could be positive or negative. Our initial velocity was 0, so that cancels out. And then 2 times negative 9.8 times negative 7. So again, we have 14 times, that's about 140. Take the square root of 140, you're going to get just under 13, 12, well, 144, yeah, so even less than that. If we punch this in, we're going to get a value of 11.7. And we have to be aware now, is this going to be positive or negative? Well, if the watermelon is dropping and the velocity is increasing in the negative direction here, our final velocity will be negative as well. So the calculator doesn't give you that, but you have to think about that on your own. And for our final value then, now we can do our sig figs. 2 is what we need. We had 3, so let's go to 2. Negative 12 meters per second. And so you could have that, or yes, you could go and say 12 meters per second down. So you don't have to include both of those. All right, and as for Kevin, the other guy from the office, playing paintball, is curious what will happen when he fires his paintball gun straight up. Paintball gun fires at a velocity of 91 meters per second, and he's holding it 1.7 meters above the ground. How high does the paintball go? So let's start it off with TAD BV. Our acceleration is negative 9.8. Our initial velocity in this case is 91. And as of right now, we don't actually know what our displacement is. We do know that it's 1.7 off the ground. So if we were to draw that, I don't know, let's go on the far side over here. You have him firing at 1.7 meters off the ground. So basically at eye level. Up it goes, and then down it goes. So we're trying to calculate it right at this point right over there. And to say, well, what is the displacement for this? How high does the paintball go? So when we calculate our final answer, we're going to have to include plus the 1.7 right over here. So we're going to have to include that 1.7 because what we are going to be calculating is just having a starting point right over here. So we can consider this to be where our reference point is, and then just shoot it all the way up till it gets to 0, and then off it comes all the way down. So when we do calculate the displacement from this point to this point, if we wanted to say how high does it go, we would also have to include plus 1.7. So we would have to add up an extra 1.7 on there. So it's going to be 1.7 plus whatever we do calculate displacement to be right over there. All right. We have one other value that we do actually know, even though it doesn't say it. At the very top here, our final velocity will be 0 for a fraction of a second there. So it slows down all the way to 0, then it increases speed in the opposite direction. So we have our final velocity, our initial velocity, and acceleration. We do not want to use one that has time in it. So the formula that doesn't is the same one as the last example, which was Vf squared equals Vi squared plus 2AD. In this case, we're going to be solving for displacement. So to isolate displacement, we'll subtract initial velocity on both sides. We will then divide both sides by 2a. And we get displacement is equal to the following. At that point, we can then plug in our values, 0 squared minus 91 squared, divided by 2 times negative 98, or 9.8. We're going to have a negative value on the top, a negative value on the bottom, so we will have a positive value for displacement. Makes sense, because the paintball is going up in direction. In this case, we have 422.5 plus, so that's what this gives us right over here, plus our initial 1.7, or 1.7. So if you do that, 422.5 plus 1.7, you're going to get 424.2. And it appears that we only need 2 significant figures, so we'll round to the nearest 10, leaving us with a displacement of 420 meters. So it ended up being that 1.7 was irrelevant in the end. Who knew? And lastly, how fast is the paintball going when it hits the ground? How fast is it going when it hits the ground? We'll start a whole new one here because I want to start just from the beginning all the way until the very end. So I want to have it where I'm literally shooting it from over here at the 1.7 above the ground. Here's the ground right here. Goes all the way up, then all the way down. And you'll see why. That way we only have to do 1 step instead of 2 steps. So we can solve it in 1 step. Our acceleration will be the same, negative 9.8. Our initial velocity was 91. That still stays the same. There is one other value. We do not know our final velocity because our final velocity at this point is negative 91, but it also is going to be traveling another 1.7 meters. So we do not know what our final velocity is. It'll be a little bit more than 91 going down. We do know our displacement. If we start over here and end 1.7 meters below where we started, we will have been displaced by negative 1.7. It doesn't matter how you travel there. So it doesn't matter if you go up, then down. It matters where did you start, where did you end, and where are you going. So we have 3 values, and we are looking for the final value right over here, VF. So same thing, we're going to be using the same formula as we did just up here. So I'm not going to write down the original formula. I will just go ahead and write down what we already wrote before, with VF equaling plus or minus the square root of VI squared plus 2AD, like so. Now we can plug in our values. We have initial velocity of 91 plus 2 times negative 9.8 and negative 1.7. Hopefully this makes sense to you too. By having this as negative 1.7 right over here and multiplying by negative 9.8, this part of this will make our final velocity a little bit larger. So not by a lot, but by a little bit. So if this hadn't been anything at all, 0, well then we know that this would have been exactly negative 91 at this point right over here. So if we go and approximate this and say this is 10, this is times 2 is 20, 20 times 1.7 is 34, square root of 34, adds quite a bit, right? Adds almost 6 or so. I'm not sure. Have to take the square root of that value though. Anyways, let's just do the math. Plug this in. The square root of 91 squared plus 2 times negative 9.8 times negative 1.7. Close the brackets. And we get a value that's very, very, very similar actually. 91.2. 91.2. And it's going to be negative because it's going down. Negative 91.2. And again, if we're going to go with only 2 significant figures though, funnily enough, that'll be 91 meters per second down or negative 91 meters per second. So and that is a little bit about calculating some of the problems with free fall notes. Now it's up to you. Good luck and have fun.